Let's talk about certain types of acid-base reactions. We're going to use what's called the Arrhenius definition to talk about acids and bases. There are other definitions, but we're going to talk about Arrhenius. And under the Arrhenius definition, an acid is something, a molecular species of the form HA, where when you put it in water, it dissociates into a proton, H+, and the leftovers, which we're going to call A-. Now A can be a bunch of atoms, not just a single atom. And so it dissociates in water, forms a proton plus whatever's left over. By the Arrhenius definition, a base is something that contains OH minus with a metal ion of some charge, and in water it dissociates into the metal ion and hydroxide, OH minus. Now the metal may be a 2+ metal or a 1+ metal. Okay, so examples of acids include HCl, which is a strong acid, and it dissociates in water and forms chloride ion and a proton, H+. Another example of an acid is nitric acid, HNO3, which in water dissociates into a proton and the nitrate anion. Okay, and these are examples of strong acids. And by strong acid, we mean something that completely dissociates into its respective ions. Okay, so they fully dissociate. There are also weak acids which do not fully dissociate, and an example of that is acetic acid. And since it does not fully dissociate, we write arrows going both ways, but it does dissociate partially into a proton plus the leftovers. Okay, so this is one that partially dissociates. And it is a weak acid. So the strength of an acid has to do with how fully it dissociates in water. Now, by the Arrhenius definition, the base includes a metal ion bound to a hydroxide, so something like sodium hydroxide dissociates in water into sodium ion and hydroxide. Again, though, the metal does not need to be a single charge. So it could be something like calcium hydroxide, which dissociates into calcium plus hydroxides. So the numbers can vary here. All right, and then I want you to be aware of what species are strong acids and strong bases. And most of the hydrogen halides are strong acids: HCl, HBr, HI. Note that HF is not in that list. And I've just mentioned nitric acid, HNO3. Another strong acid is sulfuric acid. And a third one is perchloric acid. So those are the strong acids you should know, and you can assume that any other acid would be a weak acid. And the strong bases, I will not write the full list, but it's any hydroxide that bonds to a metal atom which dissociates in water. Okay, so there's some examples of strong bases, and you should know the strong bases and the strong acids. Among the acids, we notice that some of them can lose one proton, whereas some can lose more than one. So the ones that lose one proton, such as HCl, which dissociates again into H+ and Cl-, is known as a monoprotic acid, single proton. If an acid can lose two protons, like sulfuric, it's known as a diprotic acid, loses two protons. So we can lose two H+ and form sulfate anion. And there are also triprotic acids that can lose three protons, And phosphoric acid is one of those. We form phosphate anion and 3 protons, so that is a triprotic acid. And the reaction that we're going to talk about with acids and bases, when you combine an acid and a base, they are known to neutralize each other. So these are neutralization reactions. And whenever you form an acid-base titration, you are doing an acid-base neutralization. Okay, so you take an acid, an Arrhenius acid, you take an Arrhenius base, you combine them, and you form water plus whatever the leftovers are. I'll show an example. A molecular reaction equation for an acid could be HCl, which is aqueous, plus sodium hydroxide, which is aqueous. So there's our acid, there's our base. And when they react, the H plus and the OH minus form water, which is a liquid. And then the leftovers in this case are the sodium ion and the chloride ion. So we end up with sodium chloride aqueous as leftovers. But it does form water, and that water is formed from the H plus and the OH minus form neutral water. So they neutralize by forming the neutral species water. Okay, we can write the total ionic equation for this. HCl is really a proton in chloride and water. Sodium hydroxide is completely soluble, so it is also sodium ion and hydroxide ion. We know that water is not dissociated in and of itself, so that stays as water, liquid water, but aqueous sodium chloride does dissociate, so it's actually present as a form of separated ions. Okay, so we can then look at what is the same on both sides. Sodium chloride, sodium and chloride are single species, same on both sides, which means we can ignore them. They're just watching, they're just spectator ions. And our net ionic equation is then H plus OH minus making water. Okay, and this is important. This will be, in almost every case, the net ionic equation for an acid-base neutralization reaction, because everything else is just spectator ions, and the net ionic equation will be H plus OH minus gives you water. Okay, there is an exception, and that is, maybe you want to think about what that would be. But that exception is when you also form a precipitate. I'll show an example of that. So here's a acid, sulfuric acid, and our base we'll use barium hydroxide. And when those combine, you do get water. In fact, you get 2 waters. And you also get barium sulfate, which is a precipitate. So in this case, your net ionic equation will also include barium and sulfate in addition to water. So your net ionic equation will actually include everything. There will be no spectator ions because there are no ions on the product side of the reaction. Okay, let's do some practice. Look at this example and decide which of the following is an acid-base neutralization reaction. So stop the tape and look through them and decide. All right, let's look at them. Remember that an acid-base neutralization reaction is going to have an acid and a base reacting. Okay, acid plus base. And they have to form water. Okay, so we do have water formed here. We have water formed here. We have water formed here. So we have lots of them that form water, but forming water is not sufficient to be an acid-base neutralization. You have to react an acid and a base. Hydrogen and oxygen are not acid and base by the Arrhenius definition, so it's not A. B has an acid, nitric acid, but there's no Arrhenius base here. So that is not an acid-base neutralization reaction either. Let's look at the third one. You are forming water, and you've got strontium hydroxide, which is a base. You've got nitric acid, which is an acid. It does form water, so that is the one that is an acid-base neutralization reaction. This final one involves water, it involves an acid, and it actually involves a weak base, which we haven't talked about, and it involves OH-, but it's not an acid-base neutralization reaction. Whoops. Okay, now write the net ionic equation for the answer, and you will find the net ionic equation, strontium and nitrate, neither one of them is going to appear in the net ionic equation, just the things that form water. So the product is going to be water, and to use mass balance, we have 2 H pluses and 2 OH minuses. So that is the net ionic equation. And we could take away the 2's, but we have the 2's up there. So there's your net ionic equation. All right, how do we name acids? Let's talk about how they're named. We're going to talk about 2 separate categories for how you name acids. And in all cases, acids are named based on the anions present in them. Okay, so they're based on anion names. All right, so the 2 categories are acids that contain oxygen and acids that do not contain oxygen and acids that do. They're totally separate rules. So we'll start with the ones that do not contain oxygen. All right, the rule for how to name them is you use hydro, and then the anion root, and then ic, and then a separate word, acid. Okay, what's an example? HF, that does not contain oxygen, so you use the word hydro, and this anion is F-, which is fluoride, and the anion root would be fluor, and then you put on the ic, and a separate word is acid. So this is all one word, hydrofluoric acid. Another one, HCl, hydro, the anion is chloride, so the root is chlor, and you put the ic on there, and it's acid, hydrochloric acid. Okay, so that's how you name acids that do not contain oxygen. I'll do one more. HI, hydroiodic acid. Okay, hopefully you got that. Now, if they do contain oxygen, let's look at some of these. All right, if sometimes there are a set of anions that are related to each other that are all different by a single oxygen. All right, in that case, let's look at how the anions are named first, and then we'll talk about how they that leads to the name for the acid. All right, so if you have 4, you have endings, you have roots for the anions. I'm going to do 4 roots, and the ones that can, and we're going to do kind of a chart here showing the number of oxygens going up. Okay, so the root of the anion that has the least number of oxygens will have an ending of ITE, and so does the second one. And the one that has more oxygens is named 8, and if there's 4, then the one with the most also has an ending of 8. But there are prefixes as well, and don't worry, I will show examples here that'll make this a little more clear. You have per something 8 for the anion with the most oxygens, and you have hypo something ite for the one with the least. So you can distinguish the 4 this way. All right, let's look at examples of that before I get to the acids, so that it's a little more clear. All right, we have a series with chlorine and oxygen. ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. So the names of those anions are perchlorate. Okay, so the root was chlor, so they got the per and the ate. The next one is just chlorate, no prefix. The third one is chlorite. And the one with the fewest oxygens is hypochlorite. Okay, how does this translate into the acid name? If they end in an ate, then they get the ending IC for an acid. Whoops, did not mean to do that. If they end in ite, then they get the OUS, us, ending. And they still keep their same prefix. Okay, so they end up looking like per root ic acid, or just blank ic acid. And the third one is us, blank us acid, the word acid again. And the last one has the hypo, something us acid. Okay, so let's look at all these down here. The perchlorate anion, then when you make it into an acid, which is just put a proton on there, H plus added to ClO4 minus neutralizes the charge, and you have this acid, which is called perchloric acid. The one with one less oxygen is just chloric acid. The one with two oxygens is now chlorous acid. And the one with just one oxygen is hypochlorous acid. All right. That's when you have 4 different ions that are the roots of the acids. Sometimes you only have 2. Okay, an example of that is with sulfate. Sulfate ion comes in 2 forms commonly, with the same charge and just one less oxygen. Okay, and so this one is sulfate, okay, the ATE ending, like up here, and this one is sulfite. So when you only have 2, you just use the 2 middle ones. You don't use the prefixes. So when you make those into acids, you don't need the per or the hypo. You're just using the middle ones. The ate ending becomes ic, so it's sulfuric acid. And the ite ending becomes, you say it, sulfurous acid. All right, and there are other examples of that as well. The same thing occurs with nitrate and nitrite. You can name those acids using these names.